Alright, so this is Mighty Plasma 101. We're just going to go through some of the basics of a plasma, some of the things you have to consider when you're working with plasmas, and then go into some of the specifics about Mighty, like why we're doing what we're doing and why we have the subsystems we do, and kind of how they work at a basic level. I'm not going to go into the math too much here. There's a lot of physics baked in. I will talk about kind of the scaling laws and try and use your intuition, as you visualize kind of like the particles flying around in your head. So that's kind of the level that we're going at here. There are plenty of classes, and we can talk more later if you want to go into like the derivations of specific plasma properties. It's a big field, and so we're not going to do it all in kind of the 101 sub-hour session. And we have the plasma expert himself with the cookies in the back.
Cookie.
Yeah. All right, so as those get passed around, I'll start with the basics. What is a plasma? People call it the fourth state of matter. Also, it's kind of old-timey name and whatnot. It's known as like an ionized gas. So if you think of the stages of matter, you have solid, liquid, gas. Usually people think of plasma as the next phase, where you get even hotter, and some of your free atoms or molecules get ionized. So they get even more energy imparted to them, enough to essentially knock off an electron from their outer shells, and now they become ionized. So you have free-floating charged particles. What exactly is a plasma? Ionized gas, and it has three basic conditions you have to meet. The first one is that it is quasi-neutral, and that basically means you have roughly equal numbers of positive and negative charges. And so for every positive ion, you have one negative electron. You could have, for example, a region which is all electrons or all ions, but we wouldn't consider that a plasma. The reason being, another condition that you have to meet, which is it has to display either self-organizing, or you can call it group behavior. Group behavior, which essentially means that the plasma particles respond to the plasma around them. So all of these particles have, well, not all of them, but a lot of these particles have charge, and so you can feel the electrical charge of the particles around you and respond to those. So a plasma will essentially organize itself in a certain way such that its charge is distributed over a large area. So say you have one region which has a whole lot of ions, and you have another region which has a whole lot of electrons. The plasma will self-organize itself and move in like a group way such that it becomes quasi-neutral, and now you have essentially the same number of ions and electrons in the same region. So those are two of the necessities to be considered a plasma. Another one is that plasma is dominated by electromagnetic fields. And so you can imagine, for example, in the air here, you could imagine that there's a few ions or electrons floating around here and there, right? But you wouldn't consider the air in this room to be a plasma, and this is why. It's because it's not dominated by electromagnetic forces. It's dominated by collisions, basically. And so if the plasma is dominated by electromagnetic forces, you can control the plasma using electric fields and magnetic fields. And it responds to any sort of input you apply to it with those type of fields. So these are kind of the three conditions for a plasma. It's a region with a whole bunch of ionized particles that kind of behave as a big old group, and you can impact them with electromagnetic fields. So that's the basics of a plasma. All right, so now we know basics of a plasma. Any questions on that? All right, so what are some of the properties of a plasma? Well, you've got all these particles bouncing around. There's a few things that you can know about them, a few bits of information. One is the species. So what type of particle is it? Is it an electron? Is it a hydrogen ion? Is it a xenon ion? You know, is it a negative ion? You know, those exist. Is it a positron? You know, there's like all these different, you know, types of charged particles. So, you know, you look at properties, you have like species. Each one has a mass and a charge, right? You can have certain ions, for example, with positive 2 charge. So 2 electrons have been knocked off. So you can learn about the species. What's another thing is, how about density, right? So how many are there in this certain region? Is there 1 particle in the box, or are there 10 trillion particles in the box? There could be more. Plasmas can be super dense, like you're talking about the core of the sun, or super tenuous when you're talking about like random regions of space in the magnetosphere. So certain regions of space have 1 particle per cubic centimeter, and the sun, I forget what it is, but it's at least 10, if not 20 particles per cubic centimeter. 10, and by that I mean
yeah, I was going to say, oops.
10 to the 20. So a lot of zeros. Yeah, so there's all sorts of plasmas. Density plays a big role in all the physics that go on. Another one of the properties. So you have, you know what type of particle they are, you know how many are in the box. What's one more type of property you could imagine for the particles in the box? What else could you possibly know about them? Are they sitting still? Or are they moving? Usually they have some sort of velocity, right? Like, only things at like absolute 0 aren't moving at all. So there's usually some sort of velocity where you have a group here, and you know they could be a beam. You know, it could be a beam of plasma where all the particles, say, are moving at some speed in some certain direction. It could be just very hot and they have random motion, you know, some go this way, that way, the other way, where it gets randomized by collisions, etc. But either way, there's a velocity associated with all the particles in the plasma. But that's really complicated, right? How are you going to keep track of, you know, 10 to the 20 velocities of each particle for every, you know, second? It's impossible. So generally what we do is try to simplify things and give it a velocity distribution. Velocity distributions are based on kind of the physics of what's going on. So if you make assumptions like, oh, the particles run into each other all the time and they have this much energy, then you come out with basically a velocity distribution. And there are different types based on different physics assumptions. And you can have, you know, multiple distributions within one plasma, depending on how, you know, complicated it is. But basically how it works is you have a certain velocity, and you have a certain probability that a particle has that velocity, probability, and there's some curve that looks, you know, like that, for example, where if you know how many particles have this velocity right here, you can calculate the probability that they have that velocity if you have a distribution. So this gives you a good, you know, general idea of how your particles are moving around, and so you can, you know, start to calculate things about them and like make predictions and things. But basically you sum up this, you know, crazy amount of information of all the velocities of all the particles into a simplified velocity distribution. And with the simple velocity distributions that we usually run into, like a Maxwellian is basically, you assume that the particles are in thermal equilibrium, so the air in this room would be a Maxwellian distribution, Maxwellian velocity distribution. And so for those, you can assign a temperature, and that's basically where temperature comes from. So when you hear it's like 50 degrees outside, it's based on, you know, like you could just do a Maxwellian distribution function, and you'd get like this thing, and then there's some temperature associated with this thing. And so it's the same as air, basically. You get a temperature. Of course, plasmas aren't necessarily 50 degrees Fahrenheit. Usually they're like ridiculously hot, like, thousands of Kelvin, tens of thousands of Fahrenheit, or there's a huge range. Fusion plasmas all the way down to, really cold plasmas. Anyway, these are the three basic properties you can look at for a plasma.
I was just going to say one quick thing.
Mm-hmm.
We still call the plasma that we're dealing with is cold plasma, and yet the temperature is so.
Still like what, at least 1,000 Kelvin, still 0.1.
Right, yeah, so 1 EV of energy, electron volt of energy is 11,000 Kelvin something or other.
Mm-hmm. So you'll see for like the plasma team, we talk about EV for electron temperature and whatnot, and that's because it's easier than talking Kelvin. Basically, 1 EV is a unit of energy, and it's the energy of moving a particle through a 1 volt difference. So
an electron.
Yeah. So if you're moving an electron from say 0 volts to -1 volts, because it's repelled by that -1 volt, so you need energy to move it there. The amount of energy it takes to move it from there to there is 1 electron volt. And you can convert that to temperature, and it turns out to be over 11,000 Kelvin. So super, super hot. The electrons are very, very hot.
So the temperature of the plasmas that we're going to be measuring in low Earth orbit is on the order of 1/10 of an EV.
Mm-hmm.
So,
Which is still like 1,000 Kelvin.
but that's still nonetheless, it's referred to as cold plasma.
Right. So that's the kind of temperatures that we're going to be dealing with for our space mission. All right. So those are the basic properties of a plasma. Using those things, you can learn other things about the plasma. Once you have that information, you can calculate other parameters. Here are some of the other things that you can calculate using those properties. So now we can get things like conductivity. So the electrons can conduct current, right? If you have this plasma that's dominated by electromagnetic forces, there aren't too many collisions, then if you apply a field from one side to the other, or a voltage from one side to the other, you're going to get current flow. And so you can calculate what that conductivity is based on the plasma, in this case, plasma density, and the mass of the electron. So this is the density, specifically the electron density. And this is the electron mass. So the E stands for electron, the M stands for mass, the N stands for basically number density, so how many there are. What other things can we know, can we learn? The plasma frequency. So if you take a chunk of plasma and you're able to somehow separate your positive charges and your negative charges, and you let them go, what's going to happen with these blobs here? Can anyone guess what's going to happen? Put them there, let them go. Declan?
They're going to rush back together.
Yep. So they're going to feel the electric field from the separation, and they're going to be pulled towards each other. They'll rush back together. In fact, they'll rush back together, and when they get together, they'll still have that kinetic energy from getting pulled towards each other, and so they'll overshoot, and they'll basically keep going, at which point it'll be the same situation, only reversed, and they'll feel the pull again, and they'll come back the other way, but they'll still have that initial energy, and so they'll just basically oscillate back and forth. And the frequency that happens at is defined as the plasma frequency. It scales as the square root of the density over the mass of the electrons. So you can imagine, like why is that? Well, if there are more electrons, or just more particles in general, the electric field is going to be stronger, so it's going to be pulled harder, and so it's going to oscillate faster than, if it was a weak kind of force. Another one is what is called the Debye length. The Debye length is essentially the distance that the plasma can be quasi-neutral, or the distance over which it shields. So let's say we have a chunk of metal in our plasma here. Right? And let's say that it's biased, super duper positive voltage. And we're in this conductive plasma. Right? So, we're in this plasma. What do you think is going to happen to the charged particles around here? Do you think how do you think the ions are going to move in response to this positive charge? Away. Yep. And similarly, the electrons are going to go in. Right? Because they're attracted and they're repelled. So now we have kind of these ions hanging out around this positive bias. And the ions are kind of out of there. And so you look at some region, and from the outside, you see this positive bias, true, but you also now see all these negative biases, all these negative charges, I should say, excuse me. And so from the outside, at some distance away, there are essentially enough electrons in the region that it cancels out the positive charge of the object itself. And so the plasma actually shields, it can organize such that it shields objects from the outside observer or the outside plasma. So for example, now if you have your quasi-neutral plasma out here, which remember it always wants to be quasi-neutral, there's some distance at which you can remain quasi-neutral and not be pulled in. So it self-organizes to shield out perturbations, right? And the size of this perturbation is usually on the order of a few Debye length. And so the Debye length determines, what size perturbations propagate into the plasma. And this is proportional to the electron temperature over the electron density. So for a higher temperature plasma, if the electrons are flying around, it takes more distance to basically, stop them, slow them down. And if the density is higher, then you don't need as big a region. You only need to collect, plasma from a smaller region because there's so many electrons around you. Smaller volume has the same amount of charge. So you can get these properties from your basic kind of properties, which are, again, species, density, and velocities. So, any questions on that? All right. There's a few more things to consider that I'm not going to go into the details about, but you have your plasma, you have your ions and your electrons, but usually there's some neutrals around too, just like some regular atoms, molecules, things that aren't ionized. You can collide with those, and that's going to make your plasma more resistive. Because you imagine you have your electrons, they're all trying to flow a certain way. If they hit a neutral, then they're going to get stopped, essentially. All sorts of stuff can happen with collisions, too. You can create, for example, new ions and electrons. Basically be this thing with a positive charge. you can just, scatter off of the neutral. You can excite the neutral, make it like vibrate and get all sorts of craziness out of there. So I'm not going to go into the details of that, but rest assured there are all sorts of collisional processes that you can use to make plasmas and mess with your theoretical physics. Another thing is magnetic fields. So I'm not going to talk too much about magnetic fields in the terms of like how plasmas react. But you probably know, based on like fusion devices and things, that people use magnetic fields to confine plasmas. You can get what's called a magnetized plasma, which means that the plasma behaves according to the magnetic field. It's dominated by the magnetic field. One effect from that is like charged particles, like ions and electrons, they gyrate around magnetic fields, where at some frequency and distance, depending upon the strength of the magnetic field and the velocity of the charged particle, they basically spiral around magnetic field lines and are trapped to them. So that can happen in magnetized plasmas, they're called. I'm not going to go into this too much, but rest assured that does happen. And even for our mission in low Earth orbit, there are magnetic fields, and that plays into our current collection. And if you look at Iverson's dissertation, the magnetic field does make a difference, so that's accounted for there. So that can either enhance your current collection or make it way worse, depending on how you're oriented, basically. So those are a couple more considerations for plasma that we're not going to go too much into, but very interesting effects that you can certainly study on their own. All right, so that's kind of my basics of plasmas. They have a lot of uses. They're kind of everywhere. It always amazes me like how much stuff uses them. Just some examples, like lights, for example. Fluorescent tubes. You can see them up there. They're way more efficient. Processors, etching, for example. So to make your CPU on your computer, they use usually some sort of ion bombardment techniques. So they have like a really fine-tuned system so that they can get like single monolayers of atoms the way they want them to by basically bombarding some surface with ions of an exact energy with an exact velocity that they're trying to control. There's a lot of money in that you could do. Things like coatings, you can coat glass to keep heat in. You coat your chip bag, for example. Ink doesn't stick to that like slippery plastic stuff. They treat it with a plasma that makes it so it adheres. And that's the only reason that you can do that as it is right now. Power, fission, fusion, the whole NERS department. There's all sorts of cool plasma stuff you can do there. The sun, space. The sun is a giant ball of plasma that gives us life, so that's pretty cool. It's pretty heavy and hot. Extreme plasma. Space, depending on where you are, can have like a really weak plasma or a really strong plasma. You can probably imagine close to the sun it's really strong plasma, but in the middle of nowhere it's pretty weak plasma. Another thing, thrusters and electrodynamic tethers. So electric propulsion thrusters, like ion thrusters, Hall thrusters, they're the kind of the future of space propulsion. Of course, tethers is included. And
Yes.
They're basically like more efficient. Your exhaust velocity coming out of an electric propulsion device is generally 10 times as much as like a chemical rocket without all the fire and whatnot. So huge benefits there. The only drawback, the biggest drawback being that the thrust is low. But anyway, not going to get into that too much. Let's talk about the real future, electrodynamic tethers. Yes. They offer big benefits. One of the biggest ones is they don't use propellant. So in theory, you could run them forever because you don't need to bring up a gas and eject it out. You just basically run current through whatever plasma you're in. I'll get into that in a second. But that lets you do it on smaller packages. It lets you be up there longer. It's got all sorts of benefits.
So just to ask Ryan, has everybody had Physics 240? So,
Yeah.
So they'll at least have seen.
So, yeah. I'll write down this. Lorentz force here.
Ill beats.
Say again?
Used to call it ill beats back in the day.
Ill beats. I remember. Yeah, that's,
Yeah.
isn't that a some radio, online radio channel?
Maybe.
Probably, yeah. Like
Ill
90s
beats.
joke.
If it's not Snap Up, I'll do it.
Yeah. Maybe the mighty rapper.
That's
doesn't
not
know.
bad.
Yeah, appreciate it.
This is how they start, you know. The dynasties. Yeah. So, electrodynamic tethers, you can use them for propulsion. This is how you do it. Bam, force, you can think of it as thrust. Here we have the current in the tether. Right. So you have current flowing through a wire of some length. You can put make whatever you want the vector. And you cross it into the magnetic field, the ambient magnetic field. So in this case, you'd use the right-hand rule. Let's put it on this guy. So I can say, okay, let's put the B, I guess, there. So it'd be what? I cross V is F. So you'd be having a force this way. Hopefully I did that right. Yeah, you can use it to speed yourself up, slow yourself down. You can use it to get yourself out of orbit. There's new regulations that you have to have a plan to get yourself out of space, to not be space junk within a certain amount of time. So people are exploring tethers to deboost themselves and get themselves back out of space.
The rule is for NASA missions, you have to be able to say that you'll be done after 25 years.
Yeah.
And so we had to do an analysis to say that atmospheric drag of even the tenuous environment starting at 500 kilometers would take us down within 25 years.
Yeah, for sure. But say you don't want to get brought down in those 25 years by the drag, you can use this thing to boost and keep yourself in orbit. And that's one of the main reasons we're interested is to keep ourselves in orbit, use it as orbit raising technology. Because it's propellantless, you can theoretically put it on like small packages like your smartphone where you couldn't fit a gas tank and a thruster and all that jazz. Like you can't even get close to that as it is now. So these guys offer some very distinct advantages which could let us go to smaller satellites than what's possible today. But in order to prove that and try it out, etc., we need to make sure that we can get enough force to overcome drag. So this is well known, right? The magnetic field of the Earth at certain altitudes. The length of the tether is something you can control, but you can't make it infinitely long because you're again limited on space. You don't want to be hitting all the spacecraft with your tether. And then there's drag on the tether too, so if you make it bigger and bigger, you get more and more drag, so it might not even be helping. But here's the thing that isn't known as well as we'd like. Kind of the unknown in this equation is the current through the tether. So that depends on how much current you can collect and emit from the two sides of your tether. So, for example, if we're doing net current, I drew this the wrong way. I'm going to shortcut go this way. So if we're just looking at net current here, right? We need to collect current on this side, push it down, and emit it or get rid of it on the other side. And the theory, without any sort of extra devices, the circuit here would be completed in the plasma, in the ambient plasma. So you'd be running current through this circuit. And that gets you your I and your boost. All right, so how much current are we going to collect? Well, again, with no sort of enhancing anything, we're just going to collect whatever hits either side. So the current you collect, I guess collect, just to be specific, it's going to be proportional to the flux of charged particles. It's essentially the density times the velocity. So 10 times as many particles around, you collect 10 times as many. If they're going towards you 10 times as fast, you collect 10 times as many. So it's essentially, you know, these two together. Well, the density is easy enough. What about the velocity? Well, again, you remember we have, you know, velocity distributions and temperature. So you can just do that the velocity is proportional to the square root of the temperature over the mass. So that's how your current collection scales in a broad sense. All right, so we look at this again. We say, okay, well, we got to collect electrons from one side, and we got to collect ions from the other side, right? Okay, so we look at this equation and we say, okay, well, we know from quasi-neutrality that the density of ions and electrons is about the same. Quasi-neutral plasma, so the density is about the same between those two. So that's the same, so check mark. The temperature, usually in space, they're about the same because they're collisional, so they're around the same temperature. So that's another check mark. Equal, equal. Okay, what about the masses? Well, the mass of a hydrogen ion is about equal to 1,823 times the mass of an electron. So that's a pretty big difference. You look at that, you put it in here, and you end up with way more electron collection than you do ion collection. Essentially, the electrons are light, so they move really fast, and the ions are heavy, so they move very slow. And so you get way more electrons than you do ions hitting the surface of your spacecraft. And so if you just do this, you're basically limited in the amount of current you collect by your ion collection, and ion current collection is too low, essentially. It's quite low. And so we want to find ways to enhance that and make this technology work. Also, you'll note we have these scaling laws, but really we want to predict it more in depth, and that's what Iverson did in his dissertation, what we're validating with MIGHTY, right? Like the ultimate goal is to understand our current collection to our tethered bodies. So we want to understand that to enable this in the future. All right. So let's talk a little bit about what might happen if you do put your picosat in a plasma. Okay. So we got our plasma, charged particles hanging out, and we drop in our picosat. Okay? So let's say that this thing is just the same potential as the plasma, and we just drop it in, right? What's the first thing that's going to happen here? Well, it's going to be hit by the charged particles around it, right? But we know that the electron current is going to be much higher than the ion current by orders of magnitude, at least one. So we're getting hit by way more electrons than ions, right? And so we're going to start collecting those electrons, and we're getting a net negative charge now because we're getting way more negative charge than positive charge. So we're just accumulating this negative bias, and it keeps getting more and more negative. We keep getting more and more electrons until eventually we're negative enough that we're starting to repel a lot of the electrons. So now we're negative potential, and we're rejecting electrons. And in equilibrium, we're rejecting so many electrons and kind of accelerating in so many ions that the net current is zero. And when the net current is 0, your potential isn't changing anymore. You can think of it from like a capacitive argument. Hopefully I wrote this right. Where, let's see, the voltages are, passing right, yeah, okay. So you're accumulating this charge on this side. And once your current hits 0, you're no longer accumulating any more charge, and so your voltage stays constant. Right, so charge stays constant at some negative potential where you're rejecting most of your electrons. So that's what happens if you just drop in your picosat. Okay. What's another thing that'll happen? Well, you remember from before the plasma shields itself from disturbances. That's going to happen here, where you have this negative bias. You're rejecting all the kind of electrons out, most of them. So you have all these positive charges screening the negative picosat, right? And so this region where the plasma is perturbed and the densities are off, it's not quasi-neutral, so it's like technically kind of not a plasma and acts weird. This is what we call a sheath. So if you have ever asked yourself, why do we need to get the picosat so far from the satellite? Why do we need to put the Langmuir probe out on the end of a boom? Well, this is why. You have this conducting piece of metal, and it has a sheath around it that's perturbed. The plasma in there is like weird, you've messed it up basically. So you can't take accurate measurements of the unperturbed plasma if you're inside of a sheath. So our spacecraft has one. So let's say this is the peak, I guess I've been calling it the picosat. So in this case, you have your 1 meter boom, and you have your 3U CubeSat, which is conducting on the outside from the ITO. So it also has its sheath where they can't overlap because then you perturb this measurement. And then you have your Langmuir probe on the end of a boom, which also has its own sheath. And so that's why we've needed to work so hard to get these booms and deploy everything and get it away from the spacecraft, because we need to get things out of each other's sheaths. If that wasn't the case, then we wouldn't have to bother.
Yeah, no pressure, Dayton.
Yeah. Yeah.
Wait, so Grant, that means the boom on Mighty 1 isn't necessarily about the tether?
No, it's not really. Yep. Yeah, that was a D-scope option because the complexity of the tether was slowing us down essentially. So Mighty 2, it made sense to go for the tether. But for us, it's mostly just to get it out of the spacecraft sheath so we can make unperturbed measurements of the plasma and the unperturbed current collection to our picosat, because we really need that. Yep. So that's what happens when you put a conductor into a plasma, and that's why we need all these booms and things. All right. So, any questions on that? Next, I'm going to talk about the Langmuir probe, which I drew as a weird box thing. Yeah. All right. Yeah, we'll keep that up there. Looks close enough. Okay. So, we're trying to figure out how pizza box shaped things collect current. But it turns out that simpler geometries, such as spheres and cylinders, they've been working on this problem for like 100 years or so. And those geometries are, it turns out, actually very difficult. And so for our planar picosat, we basically had to come up with empirical formulas, meaning we fit data in the laboratory and kind of make sure it makes sense in terms of the scaling laws and the magnetic field and all that. But for spheres and cylinders and planes, they've already kind of solved, what the current collection should look like. So that's why we have our Langmuir probe and why it's a cylinder, is because it's a simple geometry and they've kind of worked out what its current collection should be. So we're trying to add kind of planar shapes to that list of things that are figured out. So anyway, for our cylinder, we use it as what's called the Langmuir probe. And at its core, Langmuir probes are very simple. All you do is bias a conductor, a simple geometry conductor, bias it to some potential and measure the current you collect. But as everyone says, Langmuir probes are the simplest to use but the hardest to analyze. Because it's so simple, you need to make assumptions about the type of plasma that you're measuring, and you'll see in a second there's kind of different regions with different physics at work. So I'm going to go kind of into how we get plasma properties from a Langmuir probe from just biasing a conductor and measuring the current to it. Okay. So how do we do it? Well, like I said, go this way. We bias, so apply a voltage, the Langmuir probe, and we measure the current to it. So, when we do it for this type of cylindrical Langmuir probe, not exactly the scale, but it essentially looks like this. Okay? This is what's known as an IV sweep. So if you ever hear anyone talking about IV sweeps, or for us it's called, we call it MADS, full sweep. They're all kind of different versions of getting this curve. And using this curve, you can get all the plasma properties, well, most of the plasma properties that we talked about earlier, being density and temperature, or velocity, however you want to think about it. So, here's our IV sweep. It's divided into different regions. So I'll draw those in. I'm going to call this region 1. I'm going to call this point 2, call this region 3, call this point 4, and then I'm going to call this region 5. So the first point, way out here, or the first region I should say, we see that the voltage is very, very negative. So can anyone tell me what we're going to collect when we're very, very negative biased? Negative 1,000,000. What do you collect, positive or negative?
Positive.
Bingo! Yes, sir. Yep, you're going to get the ions. You're going to get the positive charge. And you'll remember from earlier how I was saying that the ions have very low current, right? So that's why this is 0. So that's why it's so close to 0, is you're getting very little current here, right? So it's a very small negative current, just because of the way the signs work out. And here you're getting ions. And so this is known as the ion saturation region, or regime, whatever you want to call it. I'll just say region, it's more friendly. So when you're super negative, you're getting no electrons, you're only getting ions, but the ion current is low. And so using this, and because they've worked out, the whole theory of current collection, from this you can get, for example, the ion density, right? Because down here, you know roughly how big your, you know how big your probe is, you know how much current you're collecting, so from that you can get your ion density, essentially. So that's what you can get from here. Number 2 is this point right here. And you can see that that's where the IV sweep crosses 0. So that's where you collect no current. So that's what's known as the floating potential. And that's what the probe would float to if you just dropped it into the plasma and didn't bias it at all. So it's not collecting any net current. So that's usually a few negative electron temperatures. So here, if our electron temperature was 0.1 eV, this would be like negative like 0.3 volts-ish, something like that. So that's the floating potential. It defines the transition. Oh, and that happens when you collect like some of the electrons, not very many, but enough to cancel out all the ions you're collecting. And at this point, you're still collecting essentially all the ions. So this next region here is when you're basically getting more positive, so you start to let in those electrons. So you're still a negative bias, but you're not so negative that you reject all the electrons. You're like slightly negative, so some of the electrons are getting through and others aren't. And this is known as the electron retardation regime or region, because you're retarding some of the electrons. And based on the slope of this line, you get the electron temperature. So why is that? So imagine that your electrons have like a ton of energy, right? They're just zipping around in random directions. They're really hot. So to block out all of those electrons, even the really fast ones, you need a really negative bias to slow them down and repel them. And so if they're really energetic, right, they have a high temperature, and you need a very large negative bias to keep them away from your probe. So if that's the case, then you'd have like a very big electron retardation regime. It would be like this. So it'd be like, this would be high TE, high electron temperature. So you have fast, energetic electrons, and you need a really big bias to keep them away. By the opposite, on the other side of that coin, we have, if your electrons have almost no energy, then you can, reflect all of them with like a volt or like, 0.1 volts of retarding energy. So if they're really cold, they're not moving very fast, you can keep them away really easily, right? They're not even trying to get in there. And so if that's the case, your curve would be something like this. So this would be like low TE. And so based on the slope of this region here, you can get the electron temperature. So you can know how hot your plasma is, how fast your particles are moving around. All right. 4. So that's this point right here. This is a little more hard to pick out because floating potential, it's like, okay, current 0, bam, there it is. With 4, you're essentially at the same exact potential as the plasma. And so you don't have any sort of kind of shielding here. From the plasma's perspective, there's no bias around. And so whatever particles, happen to be randomly going towards your probe will just hit it. And you're not really perturbing kind of the ambient region because you're at the same exact potential. So you're at the plasma potential. When you are at the plasma potential, you're not rejecting any electrons really. So you're going to collect a lot more electrons than you do ions. You're not slowing down or rejecting anything, and the electron current's way higher. And so you see that it's a really high electron current at this point. This gives you the plasma potential. And you can imagine, you know, if you're on the spacecraft and you know the potential of the plasma, you know you're biasing it with respect to your own potential, the spacecraft comm and the spacecraft potential. And so now, because you know what the plasma is at, you now also know what potential your spacecraft is at with respect to that plasma. So this is also a good way to measure the spacecraft potential. So that's relevant for like a lot of different missions, including ours. Later. All right. Here's the last region here. You can imagine, you know, really, really positive potentials. You're going to collect all the electrons and none of the ions. It's the same as the ion saturation region, only now you're collecting way more current because you're getting all the electrons. So this is called the electron saturation. Call it region or regime, whatever you like. And based on this location right here, you can also get the electron density. All right, so any questions on the sweeps here and what they get you? You can see that they get you a whole bunch of plasma properties. They get you the density of the ions, they get you the density of the electrons, they get you the temperature of the electrons, and then they get you the potential of the whole plasma. So that's like the reference potential for everything in that region of space. So lots of information from this one graph, but kind of interpreting it can be difficult. Yeah.
Two questions. When you increase the electron temperature, how come or the plasma temperature, how come 0.4 stays in the same place? I would think if they're moving faster, then you would be able to like have a lower voltage and still like not reject any electrons.
So you're thinking 0.4 here?
Yeah, 0.2 like moves really far to the left. 0.4
Right,
stays in the
right.
same place.
It mostly depends on your reference frame. In this situation, I was leaving the plasma potential as being constant.
Okay.
Usually that's your reference. Whenever you pick a
That makes
potential,
sense.
you need some sort of reference. So
Mhm.
in this case, you'd see that the floating potential would get way more negative if you had a hot plasma. And actually that's relevant because that's part of like the MADS, the random numbers.
Mhm.
They use stuff like, you know, they find the floating potential, and then usually, you know, the plasma potential, you know, it's like 2 to 3 electron temperatures higher. So now, if you like know this point, then you can kind of guess where this point is going to be. And so you don't have to do the full sweep. You can kind of do what it does, where it's like, okay, take one point here, flip it, just go through this thing until you find the other point here. That's pretty close to the plasma or the floating potential. Usually the floating potential is like this many volts less than the, you know, plasma potential. So start taking points here and go till here. And then those are kind of the interesting regions. The exception being this region here. Like you can imagine if you're just kind of picking regions to pay attention to, this, the electron saturation regime, I didn't write down any properties. You don't really get any plasma properties from it, so you kind of want to ignore this. So if you're trying to optimize things, then you're going to want to ignore that. The ion saturation regime, you really only need one point in it to get the ion density because it's kind of flat, depending on, you know, certain probe characteristics. But essentially you want one point and then you want to kind of ignore the rest of it. Kind of the interesting stuff happens in this region where you get the floating potential, the electron temperature, the plasma potential, and the electron density is all in this little region. So you want to kind of frame your sweeps to maximize the number of points in here and minimize the points out there.
That makes sense. So does the plasma potential stay the same then, regardless, like if you were to heat it up or cool it down, or would it change too? Or just keeping it constant as a reference point. Everything
Right.
else is compared to that.
I'm not sure from an absolute sense. Usually you use the plasma potential as your reference point, and so it'd be your floating potential and everything else that's changing.
Okay.
I mean, if you kept a closed chamber, it shouldn't change. So if you had a closed system and you heated up your electrons, you'd still have the same density of electrons around, so your local space charge would be the same, if that makes sense.
It's a pretty basic question, but
Mhm.
what is plasma potentially? Because if it's neutral, if you have the same amount of positive and negative charges.
Right,
Curious
yeah.
how that works.
Yeah, that's kind of like a weird, it's mostly a reference potential. So,
But you had given a kind of a physical definition of it.
yeah,
originally.
right.
Yeah, I forgot what you said.
Yeah, so it's the potential where you're at the same potential as the plasma around you, so that the trajectories and the velocities of the particles don't change.
It would just go right into the probe.
Yeah, they
That
just
makes
go
sense.
right in. It's hard to define in the absolute sense because, you know, true quasi-neutrality, if you define it as such, it doesn't, it's hard to say, like, because the whole planet of Earth, for example, has a negative charge to it. And so what you consider to be, you know, Earth ground is technically not, you know, absolute zero, but because everything has, it's all relative, and that's what matters in terms of the physics and what's going on. So, yeah,
Pretty safe.
it's there's no like great answer, but it's the potential at which, you know, the rest of the plasma is referenced, and so it's like 0 volts, you know, in space. Mhm. Okay. So that's our Langmuir probes. Any other questions on Langmuir probes?
Did you talk about how that slope changes with temperature?
Yes.
Yeah.
Yeah.
Okay.
Does Parker's old probe have a Langmuir probe on it, do you know?
I should get-
It does.
I got one more question.
Yeah.
So, did you say the purpose of the boom is
Okay.
just to get it out of the sheath from the satellite and the picostat?
Things kind of come in.
So, why is the
Something that
boom
comes
longer
through
than
there.
the little mast for the Langmuir probe? Or did
Yeah, no, that's a good question. For one, the picosat's a little bit bigger, so structurally it's harder to kind of do. It's mostly practical reasons, but another one is,
I'm sorry?
remember how I said that, kind of try to draw this to, not the scale, but better. So this is our primary science mission, right? And so, you know, we're really trying to get it out of the sheath. And there's also a piece in the middle of the boom here that's conducting. So, is this alidined or
Oh, you're talking about the,
The boom,
anodized?
the centerpiece of the boom.
Yeah. Does it have a sheath around it? Is it collapsed because it's not conducting?
it's gonna have a floating potential. Just
Right.
like even the non-conducting parts have a floating a sheath around it to have it so that current is equal to 0.
Right. Okay, so it has a
Because
sheath.
it's electrically isolated.
Right. But current collection can happen from kind of like any direction. Depending on if there are beam-like populations, you know, coming in, then they can be shadowed. So if there's like a beam of electrons coming in, they can be shadowed by the presence of the spacecraft. Another thing is, like we were talking about earlier, the magnetic field. There's a magnetic field here, then the primary current collection is from electrons kind of trapped to that magnetic field. And so because this is our primary science, we really want to get it away
That makes sense.
to be as unperturbed as possible. So it's kind of like a combination of things.
It's like a safety factor.
Yeah, if we could, we would put the Langmuir probe as far away as possible,
Mhm.
but you know, we couldn't getting it on this boom. You know what I mean? Like,
I know.
there was no room. Yeah.
Linear probe's not as important.
No, it's just smaller. So
Yeah.
Yeah, no, there's a scientific reason.
I think proportionally, if I remember the numbers on our sheets right, it's actually they're not too different in the amount of space we have for those sheaths.
Yeah, but like one of the issues is that, well, the picoset's bigger, A, and B, it's going to be biased to a bigger potential. So the
Mhm.
sheath size can change based on
Yeah, that makes sense.
how much you bias it. Essentially, the potential scales as the exponential of the negative distance over the electron temperature. And so if your potential's 10 times as high, then you're still going to be affecting it more further out, if that makes sense. Kind of grows and grows to try and get all of the plasma. And so this thing can go up to 200 volts, and this thing can only go to 10 volts. So the sheaths will also be different size. Again, we would like to get this further out, but it's just it's tough.
It's logistical.
I understand.
Yeah. So for this mission, it made more sense to put the one boom we could fit, we would put the picosat on it. Okay. All right. Quick thing on spacecraft current balance, and then I'll be done. I know I've been going a while.
Mhm.
So, in the same way we were talking earlier, where the picosat or chunk of metal that you put into the plasma is going to change potential until it collects zero current. Everything on your spacecraft is connected together, and it's going to do the same thing. Or essentially, in the steady state equilibrium, the summation of all your currents to your spacecraft is going to be equal to zero. So this includes the current to your spacecraft main body, your spacecraft, your current to your picosat, your current to your Langmuir probe, your current, all your other current sources, for example.
Emission.
Yep. And this is the reason why we have that subsystem there, the cathode. So summation of the currents has to be zero. We're going to be biasing our picosat to like 200 volts. When we're biasing it to 200 volts, we predict it's going to collect up to, what is it, like 5, 6, I'll call it 5
milliamps.
milliamps of electron current. Yep.
Primary science is 1.5 milliamps for electron emission minimum. Sorry.
Right. So if this is 5 milliamps and this thing is off, right, like the Langmuir probe, let's just say it's off because we're doing our other stuff. That means that our spacecraft main body has to collect 5 milliamps. Well, our spacecraft main body has to collect electrons because this thing, or collect ions, because this thing's collecting electrons. And so to cancel each other out and equal zero, they have to be opposite signs. So for our spacecraft to collect 5 milliamp of ions, you basically, you kind of can't do it. The potential would have to be, I don't know, like 1,000,000 volts or something. It'd have to be astronomically high.
Not astronomical.
Yeah.
Or you could just chuck it into a denser plasma like the sun.
Yeah, but then imagine what this will do.
So did you talk about, I forget, did you talk about for ions, the RAM versus thermal velocity?
I didn't get into the RAM velocity. So the dominant ion collection mechanism in low Earth orbit, which is where MIGHTY is going to be, is actually the RAM component. So here's your spacecraft. You have all these ions that are kind of basically at rest, right? And they have a pretty low velocity, at least compared to the electrons and compared to your orbital motion. So in LEO, I think it's around 7 kilometers a second for our altitude,
7.5.
7.5. So let's assume we're a little higher up. But basically, because you're moving fast, because of the relative velocities, it appears like the ions are moving fast towards you, you know, like you're in a car or something. And so, you know, if you just change your reference frame to that of the spacecraft, you get these streaming ions. And essentially the current collection due to the streaming ions is greater than the collection just due to their random thermal motion into you.
So that one arrow that you just had, the third arrow that you drew up there, that's down at 45-degree.
Yeah. And so I guess to be more clear, let me make it more to scale, where these guys are streaming in, and so there's a relatively large flux compared to the thermal component, which is very small. And so your current collection is actually dominated by the RAM ion current.
So I think the numbers is around a kilometer per second for the
The thermal
thermal
velocity.
and, 7.5. So it's, it's not teeny tiny, but it's,
Yeah.
it's
They're
a
comparable, but this dominates over. So you need to account for both, but this gives you significantly more ion current. But you still need a really large potential to do this. Just kind of,
Or a very high velocity.
yeah. So we got a problem here. We can't collect 5 milliamp of electrons, or we can't collect 5 milliamps of ions. And so what's going to happen? Well, what's going to happen is this will be limited to whatever this is. So say we can get, I don't know, 100 microamps of ions. Well, then we're only going to collect 100 microamps of electron. And so, what's the potential things this happens at? Need to draw a block diagram of that. Because everything's tied together. Here's your picosat. You're biasing it positive with respect to your 3U. And then there's some sort of potential difference between 3U and the plasma. So, how do I draw that up here? So essentially what happens is you apply your 200 volts to this guy. So now your picosat is 200 volts positive of your main body, right? We're going to do this during the mission. The only thing is we don't necessarily know unless we try to figure it out, which we are trying to figure it out. When you apply this 200 volt bias, what is your potential relative to the plasma? Your plasma. And I'll just do that to give it some sort of potential.
Plasma.
Yeah. It's very important. So what is this? Well, if you're limited by only your ion collection to your main body here, then you can't collect very much from your picosat. and you can't collect very much, so your bias relative to the plasma has got to be pretty low. So to collect 100 microamp of electrons, say you need to be, plus 5 volts with respect to the plasma, right? So we know this is plus 5 volts with respect to the plasma, and it's 200 volts positive of the 3U, and that means that the 3U is negative 195 volts with respect to the plasma. So now we see that we can't bias our picosat truly to high potentials unless we find a way to fix this situation, to get enhanced ion collection. And one way that you can get enhanced ion collection is by not collecting ions but emitting electrons. Emitting electrons, getting rid of your negative charge, is the same as collecting positive charge from a current standpoint. So to remedy this situation, we add low. Instead we add another current term. In fact, I'll say, let's make this here. And let's just emit electrons to balance out our electron collection, and then we won't be charging up our spacecraft at all. So the spacecraft will just be whatever it is naturally, its floating potential. So that's a way that we can actually bias our picosat to the 200 volts. Because now, if our picosat is actually at 0 volts, it doesn't get charged up by collecting electrons here because we're emitting the same number, then we actually have 200 volts on our picosat, which is what we want because we're trying to measure the current collection up to high biases. So that's why we need our thermionic cathodes, because it provides the electron emission term. If we didn't have that, we'd be handicapped to just whatever the ion collection is, essentially. So we'd basically be measuring the ion collection current to the spacecraft here, as opposed to the electron collection at high biases on the picosat, which is what we really want. And so that's why we have the thermionic cathodes. We're trying to emit electrons to balance the electrons we're collecting on our picosat. Any questions on that? Yeah.
So on that IV curve you drew over there, after we get past 0.4, you have the I collected just kind of flatlining. Is that actually what happens, or because I know the Langmuir probe goes to like 10 volts at the most?
Yep, that's a really good question actually. So in theory, it's supposed to flatline. The idea being that you're collecting all the electrons around you, no more. But that depends on the theory that you're using and the relative dimensions of things. So this theory here, where it flatlines, essentially assumes that your sheath is tiny, that it's minuscule. It's a thin sheath. It's called thin sheath theory. So that means that your sheath is like this big, right? So it's the exact same size as your probe. So if this is the case, once you're at the plasma potential, you're already collecting all the electrons that are coming in. And so if you bias it more positive, you don't get any more electrons because you're already collecting all the ones that kind of randomly go into your sheath. You collect all of them, you're good to go. Doesn't matter how positive you get, you can't suck them out of here because it's shielded again. So from the outside the sheath, you can't see it. So it's just whatever electrons happen to randomly thermally kind of walk in. But what if your sheath is really big? Instead of that, it's this or bigger. You get the idea. So now, if your electron comes in from, say, up here with some velocity, there's some random, well, not random, you can kind of estimate whether or not it's going to actually hit your probe. Because there's a chance that it comes and hits your probe. There's also a chance that it just gets bent a little bit and just keeps on going out the other side, for example. So if you looked at it from another angle, if you looked at it from the top down, top of the cylinder down, there's your probe, here's your sheath, here's your electron coming in, and say it's going this way, well, it might get attracted, but go around and just miss, right? But if it had some velocity like this, then it would go and get collected. So there's some probability that it gets collected, even if it does enter the sheath, and there's, by the same token, some probability that it leaves the sheath and never gets collected. And that depends on the potential. So if this thing is like, you know, a megavolt, then the velocity of this when it enters the sheath doesn't really matter. It's just going to get way sucked in, right? It can't fight against that. But if it's like plus, you know, little m, a millivolt, well, now it barely knows it's there. So now instead of doing that, it's just going to kind of like just keep going and not even care. So you can see with this type of scenario with a big sheath that it does depend on how positive you are, because you're not collecting everything that enters the sheath. With this one, anything that gets in the sheath, boom, you got it. With this one, maybe you get it, but it depends on the potential. And so for thin sheath theory, it flatlines. For, this is called orbit motion limited, or OML. So this is an orbit. It looks like you're orbiting like a moon in space with a spacecraft or something, right? Orbit motion, and the collection is limited by your orbital motion. Hence the name. So OML. So for OML, you know, it might look like this or something. So actually finding this point can be very difficult. If it's like a very ideal plasma, you can a lot of times just find it by looking. Be like, oh, it's there. But for, you know, these more OML big sheath issues, it can be very difficult, and sometimes it isn't even possible. But yeah, I mean, it can be almost impossible. The best way to find this generally is to take a derivative of this curve, and where the derivative like peaks, that's where you have a change in the like way the slope is changing. So there's like a change in physics, and that's where you switch from electron retardation to some OML collection scheme, because they have different, you know, functional forms. So depends.
Yeah, that makes sense.
Yeah, this is simpler, right?
Mm-hmm.
It gets close, you get it. With this, it's like, oh, geez, you gotta do the energy and conservation of angular momentum nonsense. Yeah. Cool.
Yeah, I'm just gonna say that, so another version of this is that it saturates when, if the sheath gets bigger, it can't capture any more electrons.
Mm-hmm.
So if you just had an infinite plate for the sheath, it just expands out from the plate. There's no place, just because the sheath got bigger, there's no additional electrons get in. You've collected them all. So that so that means it's saturated. And so that's a 1D sheath.
Mm-hmm.
And there's versions of this. It's a two-dimensional 2D sheath, and it like an infinitely long wire. And what happens as the sheath expands? Well, there's electrons that can be captured, again, depending upon the temperatures and all that. And then the 3D sheath would be like if you had a sphere, you're trying to collect the sphere. So the sheath expands in not just 2 dimensions, but in 3 dimensions. So you'll see a third line coming from the plasma potential point. That's, you know, they're saturated. There's one for a infinitely long wire effectively, or a sphere. And there would be those three cases.
Mm-hmm.
And for us, with our Langer probe is a short cylinder.
Yeah.
And so it's somewhere between
These two, right?
between those two.
Between a sphere and an infinite
Yeah.
cylinder.
If you get if you get the sheath big enough, this little cylinder in the middle, whether it's a cylinder or a sphere, you really can't tell any difference. So
Mm-hmm. Yeah. That's another good effect, though. Yeah, is like if you increase the potential, according to this, technically your sheath can also grow as well, which is another violation of the thin sheath theory, but that also contributes.
Makes
That
sense.
and OML and the sphere versus infinite cylinder.
Makes sense.
So I feel like I've done my job of bringing cookies. And between David and Declan here, there's three of us.
Okay, do you want to have him?
Oh, okay.
Dustin, you want
Nah, I'm good.
last
I have-
chance?
Go ahead.
Of course,
Grant needs at
of course
least,
Grant
uh,
needs,
Yeah.
Grant needs a couple.
Refuel. Anyway, if there are no more questions, call it a night, I guess, or a plasma meeting. Or...
I'd agree. Thank you very much, Grant.
Thanks, guys. Yeah, appreciate it.
I've definitely learned a lot tonight, even.
Wonderful.
So,
Wonderful lecture.
Thanks,
Hopefully that
Grant.
was and hopefully
Thank
that was
you.
informative for you guys. And Kate, thanks for
Absolutely.
coming, man. Appreciate it. Even though you
Always likes to learn more.
Yeah. Well, now you know hopefully some more about plasmas and the mighty mission.
and we will see you when you become internet famous off of this recording.
Oh,
Oh,
there you go.
jeez.